So, folks, welcome to the session. And as a disclaimer, I'm not an author, so slides are not my own. So I made a few changes just for my understanding. But one of the things I'll tell you is that it's a very interesting paper because I learned something about it. So the overarching goal is to talk about end-to-end messaging applications and their authentication ceremonies. So when I read the paper title, I tried to guess. So I didn't understand what was authentication ceremonies. So that's what I learned about it. And the common misconception, like security researchers like I had, about how Signal and other protocols actually work. Okay, so this is the outline of the talk. So we're going to talk a little bit about background. We're going to start from the very basic about secure communication. Then I'm going to talk about the author's contribution, claim contributions, how they systematize the existing work. And then we're going to talk a little bit about the actual findings regarding authentication ceremonies. Finally, I'll conclude with their concluding remarks. Okay? So now, let's talk a little bit about secure communication and why we need it. So in the time of, say, revelations of what Edward Snowden released, there seems to be and with a lot of surveillance, what we need is an end-to-end encryption so that we can securely communicate with each other. Okay? Now, there are cases, so I want to distinguish this from airdrop, where you can put a tip to a journalist that has to give you one-way guarantee, where we are talking about chatting, like Signal, audio call and video call. Okay? Now, let's start from the very basics. If we have Alice and Bob wanted to communicate, one way they can communicate is use a service provider where Bob essentially use an encrypted message to the service provider, who essentially routes it. Now, if you have taken security, this is bad. It's not, like, at least in 2023, this is not going to work, right? Because, just to be explicit, the service provider actually can read the messages. You can have a wiretapper. Your ISP can read this, or you have government surveillance. Okay, so this is undesirable. This is not going to work. Now, what we want, especially for this secure communication, is none of these interceptors be able to read what me and my wife are talking about. Okay? So that's something we would like. Now, what are some such properties? So the properties are confidentiality, obviously, integrity, which says nobody can modify it without one of the endpoints being able to detect it, and authentication. That is, I am actually talking to my wife, not somebody else, right? Now, as I will go on a little bit details, that there are other properties we might need on top of these three kind of guarantees. Now, if we think about how do we go about setting up an end-to-end channel, one possibility would be that we have a pair of shared keys. So each user shares a symmetric key on the service provider side. And then what you could do is you essentially, the service provider, you can use the key that you have with the service provider to encrypt, and then the service provider decrypts, re-encrypts with the other shared key, and sends it over. Now, this is not end-to-end encrypted because even though you can protect against a wiretapper or a government surveillance, you cannot protect against the service provider. So this is not end-to-end. For end-to-end, what we would like is go to a more public key setting. Let's assume Diffie-Hellman, where to the service provider, you essentially, both of the participants provide their share during initiating a chat session, and then the service provider provides those to Alice and Bob, who can use that to derive a shared key. Okay? Now, in this case, the service provider cannot actually read this because they don't know this KAB, thanks to Diffie-Hellman, like the properties of Diffie-Hellman, right? But here is a classic problem, that is very well known, is that it's not going to work with wiretapper, government surveillance, but the expectation seems to be that service provider, we can protect against the service provider. Turns out you cannot, because this is a very straightforward man-in-the-middle attack, because you don't have authentication of the public key, right? In that case, you could have a situation that this middle person creates two kind of a connection rather than an end-to-end connection by swapping their public key. This is a very typical attack against man-in-the-middle against Diffie-Hellman. So this is where the authentication ceremony comes into play. So that is, somehow you need an out-of-band channel to verify that you are talking to the right person, endpoint. And this is their particular key. And for that, what you could do is you can talk about somewhat like a hash of their public key represented in a QR code or a sequence of numbers. This is what we mean by, the authors mean by authenticated ceremony. Okay, now that being said, as I mentioned, we would need, at least end-to-end chatting, we would need additional properties. So one such property would be perfect forward secrecy. That means somehow during communication, if your key gets revealed, the attacker cannot read anything in the past. Okay? So that's, I know it's called perfect forward secrecy, but sounds backward. And the other one you want is deniability. That is, I've never sent that message. Right? So to achieve this, there are these protocols that people have offered. One is by Nikita Borisov, where the high-level idea is that you start off by sending your Diffie-Hellman share, A, Alice, and B, Bob. And once you are done, what you essentially do is while you're sending the message, you start with the next round's key. So this way, it's perfectly forward secret, hopefully, as long as you can authenticate G raised to the X1 and G raised to the Y1. Right? If you do that, every key is, every message is using a different key. Okay? Now, and so an extended version of it is this signal ratcheting. This ratcheting idea is this: they use this extended, triple extended Diffie-Hellman, where you essentially, the senders have a sequence of keys to send messages, and the other participant has a sequence of keys. So, and it changes every time over, like, for every message you send. Okay? Now, for real-time, like video or audio, one of the protocols that is used is Zimmerman real-time transport protocol, where it does Diffie-Hellman. The only change is that they have this short authentication string. That's because this is being used in audio. One of the participants can say it out loud that, by the way, for this session, the short string is like XYZ, and if the other party agrees, then you're good. So that way you are bootstrapping trust of the public key. Now, so the claimed contributions of this paper are twofold. So the idea is that they're trying to understand what underlying messaging protocol they're like this commonly used end-to-end apps are doing, and how are their authentication ceremonies. And particularly for the authentication ceremonies, they are thinking about the security and usability, right? And this is where the interesting aspect comes into what I learned. I'll show you what I mean in a bit. Okay, so before I go on, the authors wanted to kind of, in this slide, show what is the systematization methodology. So they kind of put the tried Android Google Play Store, and based on rating downloads, they got 19 apps. And so these 19 apps can be categorized into like Signal family and everything else. So everything else is these proprietary protocols, like say FaceTime and others. say, Telegram uses its own custom protocol, which was broken, I think, in last Oakland? Yeah. So there was a paper by Kenny Patterson that shows that the claim security guarantees are not available. Now, how are they organized? So the organized is what features are available. Features mean chat, audio, video, or group calls. And then group scenarios in like what kind of security they provide in the group call settings. What are the authentication ceremonies look like? What are the key fingerprint if authentication ceremonies are there? And like what it entails to perform the authentication ceremony, and are there out-of-band channels with which you can perform this authentication ceremony, possibly with SMS as an example. Okay, so now the surprising part. So they use, all of the apps by default use this aspect called opportunistic E2 end-to-end mode. That is, you set up a tunnel without ever authenticating the public key, right? But if you were to see the screen, and it says messages and calls are end-to-end protected, right? In WhatsApp on your left, right? And in that case, so I thought this is already, everything is authenticated, bootstrapped, and it's not. It's so whenever you start chatting, this is what shows up, right? But the hope is that afterwards you are going to do this authentication ceremony to actually validate this. And I double checked it in Signal. Signal does the same. Okay, so one of my students have been talking in Signal over. I've never verified him, so I've never kind of done the authentication ceremony. And so most of them by default use this. And so people might think that they are getting the full benefit of end-to-end encryption, which they are not. They might be talking to somebody else, right? Now, so again, these messages are somewhat confusing. They are saying that they are end-to-end encrypted, which is, but you're not you're not authenticating the other party. The opportunistic E2E end-to-end mode here, essentially you would have a pair. It's essentially you give each of them the share, defilement share, and you provide this, and based on it you set up a key. But if you don't authenticate the public keys, you could do the cute replacement attack by saying setting up two actually control channel instead of end-to-end encryption. So this is what TLS interception does, right? So if you think about TLS interception, that's exactly what happens. There is a middleman who essentially creates two TLS connection to both parties, but both parties think it's end-to-end encrypted. Okay. Now, so in many cases, if you open up Signal right now, you would see numbers not verified. So if you click a number verified, you will be ended up given something like this, which is the fingerprint of the public key. And you are supposed to match it with the other party, right? And in that case, this is what we mean, like this paper mean about authenticated ceremony. It's essentially, so every time we think about TLS and other things, we bootstrap first, then communicate. Here you start communicating and then bootstrap, right? It's the other way around. Now, again, because this is human dependent, you're waiting on the human, relying on the human to do the verification. The representation of these fingerprint actually matters, right? So this is why the authors of this paper also talk about usability issues, whether certain fingerprint representation are usable, are there, like what are the implications of human errors, and do they support the apps in question support out-of-band channel, like sound, SMS, email, right? And the main result is depicted in this two tables I'm gonna show. Now, I'll try to read it because this is not what you're used to. So I think the first set of columns, can I point right here? So they talk about what are the default end-to-end mode. So if you see, a lot of them are about opportunistic by default. Am I? No. So, let's see. Okay. Does it work? Okay, doesn't matter. First column is what type of protocol they are using. A lot of them are either proprietary or signal family, right? The second one is the end-to-end encryption mode. In many cases, this is opportunistic by default, and after ceremony, it becomes real end-to-end. And the next three columns show that whether they support chat, audio call, or video call, and then what happens in the group scenario, the second set of columns. And are they vulnerable to active man-in-the-middle? Turns out all of them are, because by default you don't do any ceremony. Okay? Now, but the question then becomes, okay, let's understand, by default you are susceptible to man-in-the-middle, but is there a way to move to an encrypt, like authenticated setting? Turns out in many cases you can, as long as you perform these authenticated ceremonies, except three cases. One is FaceTime, the other one is Google Meet, and the third one is messages by Apple. Right? In these cases, there are no way to switch in the middle of the communication of the authentication, which I didn't know. I always thought iMessages were very secure. Now, the next aspect is regarding the usability of authentication ceremonies. There isn't it's too many information. Let's switch to the summary slides. And so here, so only when you have done ceremonies is when the classic understanding of end-to-end is given. Otherwise, it doesn't. And users, even myself, was unaware of this aspect of authentication ceremonies. And in many cases, I felt misled, like cheated. Like when I've been talking to my student for 2 years, I've never verified his number or like this authenticated ceremony, right? And what are the chances that this would happen for regular users? Okay. Regarding usability and human errors, users again are vulnerable to man-in-the-middle due to usability issues. If you didn't know about it, some of the users actually do not have an understanding. I can actually take that to some users, to administrators, had no knowledge of this usefulness of fingerprints, and users often took significant time to actually locate and complete this authentication. And so the last bullet, users are vulnerable to man-in-the-middle. I mean, that's true. And this is my personal philosophy, at least when doing research with my colleague Siu Chow, is that never let a human do a machine's job, right? Let machine do a machine's job, not a human. Now, the fingerprint representations, they come in two flavors. Either they are pictorial, QR code based, or a sequence of numbers, right? And in many cases, for Zoom, when you're doing it in the group setting, the meeting host is supposed to read it out loud, and everybody else who's listening in is supposed to validate that these are the right numbers they're seeing on their side. That way, this whole end-to-end connection guarantees are achieved. But the second bullet, I left it, so I wanted to deviate from that. So they said that attacker could sit and record the meeting host voice saying 0 to 9 and then somehow change it on the fly. I think that's something we don't have to worry about, honestly, right now. That's a little too futuristic, even for my taste. Now, that being said, the authors examined 19 end-to-end encrypted applications, which they claimed, and 6 of them turns out they do not actually implement the end-to-end encryption as we understand it by default, and most of them do this characteristic, this opportunistic end-to-end, which makes them susceptible to man-in-the-middle, classic man-in-the-middle attacks, and users often don't do these authentication ceremonies because they are hidden deep inside this option jungle. And One of the other things they said was that half of the end-to-end encryption application do not have an out-of-band channel with which two users who are far apart can do this exchange of this information. Finally, Google Meet, iMessage, and FaceTime do not give you a way of verifying any method to verify user fingerprint. Now, that being said, thank you. If you have questions, please don't ask me. Ask the authors.